definition. We're going to be talking about continuity, so we need to know what it means for a graph to be continuous. And basically, it's continuous if you can draw that graph without picking up your pencil. Okay, that's a very informal definition, but it works. This graph would be continuous because I can draw that without picking up my pencil. If I did this graph, would that be continuous? No, because I had to pick up my pencil to jump from this piece to the next. So we can give intervals where something is continuous, and that will just be like when we're doing domain and range. The only time we use y values is when we're talking about a range. So we'll give an interval of x values if I want to know where something is continuous. So if I'm looking at this one, determine the intervals of continuity. I apologize, it is a little difficult to tell there, but on A, that is an open circle at 0, 2. So you might need to kind of draw that in on your paper. So can you first just tell me where this graph is not continuous? Yeah, right there where I have my open circle. There's a break in my graph. So where it is continuous is everywhere but that point. We give an interval using x. So it's coming from negative infinity if you go left to right. And it stops being continuous right here, and that's when x is 0. And after that point, it's continuous again, so union 0, infinity. Now, why would I have put an open circle at my, or a parenthesis on my 0 there?
It ain't touching.
Right, it's an open circle on my graph, so it doesn't touch it, it can't get a bracket. All right, if I look at B, where is that one continuous? Everywhere. So we would put negative infinity to positive infinity. All right, you guys do C and D for me real quick. Write down where those are continuous. What do you think for the first one? Where is it continuous? Union 2 to infinity. It's continuous everywhere except at that open circle at 2. And D? Everywhere. No breaks in the graph there. All right. We can also talk about if functions are increasing, decreasing, or constant. So just like with a line, if our line is rising, it's increasing. Falling is decreasing. Constant is like a horizontal line where it doesn't change. With these, we're talking about as you go from left to right. So this is an increasing line, decreasing line, constant line, just your horizontal. So we are going to look at some common graphs. We are going to first draw the graphs, and then we're going to use that graph to answer questions. Domain, range, increasing, decreasing, all of those kinds of things. So here is our first one, the identity, f of x equals x. If I asked you to graph this, what is it going to look like? Yeah, it's just like y equals x, that's a line, isn't it? We just got done taking a test over that, we know how to graph a line. The y-intercept is? Think about y equals mx plus b. The y-intercept is 0, slope is 1, up 1 over 1. You could also make a t-chart if you ever needed help with graphing those. So first we'll draw our graph. So it's just this. Oh, pretend my line is straight. Sorry about that. Sometimes I'm better than others. Domain. As I go from left to right, what x values do we use? The range would be same thing. On your notes handout, I had some other things. So is this increasing, decreasing, or constant? increasing. With that, we are going to give an interval for x values. So our increasing is negative infinity to positive infinity. Is it ever decreasing or constant? No, so just ignore those or draw a line through them. It's never. Where is this graph continuous? Everywhere. So negative infinity, positive infinity. Really interesting. Lots of infinities there. Let's talk about the square function. F of x equals x squared. Do you know what this graph looks like? Well, if we don't know, what can we do to get it? T-chart. So what is, if I put in 0, 0 squared is 1, 2. Okay, if I put in some negatives, negative 1, negative 2. Alright, so let's pop these. 0, 0, 1, 2, 4. If I put in 3, 3 squared would be 9. Negative 1, 1, negative 2, 4, negative 3, 9. So this is a parabola. The domain here. As you go from left to right, this part will keep going to the left, that keeps going to the right, so what x values do we get? Your range is your y, so going from the bottom up, this graph starts at 0, it hits it, so that would be a bracket, comma, keeps going up forever, so it goes to infinity. Okay, if I'm talking about going from left to right, what does my graph start off doing? Decreasing. If we give the x values, it's coming from negative infinity. Where does this graph stop decreasing? At 0. So let me mention something there. Technically, it is not going to matter if you put a parenthesis or a bracket on the 0. It's a closed circle on the graph, so you could put a bracket. When you go to Math Excel on this section, it will say give the open interval where it's increasing or decreasing. Because at just a point, if I'm just looking at the point 0, 0, that point itself doesn't go up or down. So when Math Excel says give the open interval, they want you to use parentheses. Technically, it doesn't matter. Parentheses or bracket, they're both correct. But just know when you do the Math Excel, the directions will say open interval, so it wants a parenthesis and it'll count off if you do the bracket. It's just one of those things that I can't change in the Math Excel, but there's really no difference in the notation. After 0, what starts happening? Increasing. So that's starting when x is 0, and it never stops, so that would be 0 to infinity. Is it ever constant? Do we ever have a horizontal piece? No. Where is this graph continuous? Yeah, it's always continuous. From negative infinity to positive infinity. Right. So far, so good. Let's talk about the cube function. So if we don't know what it looks like, we know we can make a t-chart. You put in 0. 0 to the third is 1 to the third, 2 to the third, negative 1 to the third, negative 2 to the third? Alright, let's graph it. So, domain. As we go from left to right, this will keep going in both directions, so it is your range. This end's going down forever, that end's going up forever. Alright, increasing, decreasing, constant. What is this graph doing? Increasing the entire time. So you can mark off your decreasing and constant. Where is this graph continuous? Everywhere. There's no breaks in this graph. Seems to be a common trend on all the graphs we're drawing so far. No breaks in them. So far, so good? We have 3 more common functions to look at. Thank you. I don't know what happened here. All my stuff shifted. Alright, so square root function. If we don't know what it looks like, we know we can make a t-chart. Can you plug just anything into that? No. We can do a 0. Square root of 0 is 0. Square root of 1 is 1. What's another nice number we can take the square root of? 4 will give me a 2. Square root of 9 would be 3. Can you do negatives? No, they'd be imaginary. So this is all we can do. So 0, 0, 1, 1, 4, 2, 9, 3. So the domain on this. As we go from left to right, what values do we hit? Subtracts at 0 and keeps going forever, so it goes to infinity. The range, bottom to top. So the lowest value we hit is 0, and it keeps going forever, so that would be to infinity. Increasing, decreasing, or constant? Increasing. It is rising. It's slowing down, but it's still rising, so it's increasing the entire time. Is it, and where is this continuous? Everywhere. Next one, cube root function. So I can plug in, we can do the cube roots of positive or negative numbers. What is the cube root of 0? 0. Cube root of 1? What about the cube root of 8? 2. What about cube root of negative 1? Negative 1. Cube root of negative 8? Do you guys know where I'm getting these numbers? Like if I put in the 8, do you understand where I'm getting the 2? Just plugging it in. You could use your calculator if you ever had one that you got stuck on. You could put in numbers that didn't come out as nice. I'm just trying to give us good points on our graph. Alright, domain. What x values does this hit? Range. What y values does it hit?
Negative infinity above.
Increasing, decreasing, or constant?
Increasing, decreasing.
As I go from left to right, it rises the entire time, so it's always increasing. Where is this continuous? Everywhere. Last one of these I want to talk about. Absolute value. What does absolute value do? So if you put in 0, the absolute value of 0 is? If you put in 1, 2, 3, negative 1, negative 2, negative 3, 3, this is just a V. So what is the domain here? As you go from left to right, it's extending both directions. So negative infinity to positive infinity. And the range, what y values do we hit? Bracket on the 0 and it goes to infinity. Okay, as I'm traveling from left to right, my graph starts off doing what? Decreasing. That's coming from negative infinity and stopping when x is 0. Again, technically it could be parenthesis or bracket, but the math Excel will say use a parenthesis. After that, what does my graph do? Increases from 0 to infinity. And this graph is, again, always continuous. No breaks in this graph. Okay. Questions? Let's talk about this. X equals y squared. If I wanted to graph that, what would we have to do?
Get y values off.
Okay. So you can solve for your y, and that would work. If you wanted to make your t-chart without solving for your y, then it would be easier to pick your numbers and put them in for the y itself, and that would also work. Let's just go directly to our t-chart. That would be faster. So let's just plug in numbers for the y. Let's do some negatives, some positives, see what we get out. So if you put in a negative 2, then x is y squared, so negative 2 squared is 4. If we put in a negative 1, we get out. If we put in 0, 1, 2, tell what this looks like? We're getting a sideways parabola here. Is that a function? No, fails the vertical line test.
Couldn't we just tell right off the bat?
Yeah. If you have an even power on your y, then it's not going to pass your vertical line test. So let's talk about symmetry now. So you probably are going to have to get out some notes to finish this, or get out notebook paper, because I gave you definitions, but I didn't leave room for the examples. I was trying to save some trees, I guess. So when we're talking about symmetry, the definition I put on your handout tells you it's symmetric to the y-axis if replacing your x with a negative x gives the same equation. So f of positive x equals f of negative x. Okay, in other words, what that says is if your original graph has the point, let's say 2, 3. If it's symmetric to the y-axis, what other point would have to be on this graph? Negative 2, 3. If you flip it over the y, you have the opposite. So both a positive x and a negative x have the same y value. Your homework. The first question, I'm going to give you a point. I'll say, the 2, 3, and then I'll say, okay, if it's symmetric to the y-axis, what's your point? And so just realizing that's just like flipping it over the y, so it makes your x negative. If it is symmetric to the x-axis, so let's just use that 2, 3 again. If it's symmetric to the x, that means I can flip this graph over the x-axis and it overlaps itself. So what's my point that I would have to have? Positive 2, negative 3.
Yeah.
So if it's symmetric to the x, both a positive and negative y have the same x value. Okay, symmetric to the origin. So if we take the point 2, 3. If it is symmetric to the origin, that means I could flip this over both the y and the x to make it overlap itself. So what it does is it changes the sign on both the x and the y. It's like 2 flips to make it work. I just gave you examples using single points, but we could talk about it using complete functions as well. If I said symmetric to the y, it'd be like a parabola. If you fold this thing on the y-axis, assuming my lines were good, then it overlaps itself. Symmetric to the x, that's like the example we just did. The x equals y squared. You could fold it on the x and it overlaps itself. Symmetric to the origin, that would be like your cube function. If you flipped it over both the x and the y, then it overlaps itself. Going along with this, we have some terms, even and odd, that come up. And these only apply when we're talking about functions. If something is symmetric to the x, is it a function? No. If it is symmetric to the y-axis, we call that even. If it's symmetric to the origin, we call that odd. So that was the last slide of definitions I put on here. But basically, even goes with the y-axis, odd is origin. I remember the O's go together. So if it's symmetric to the origin, we call that odd. So as far as deciding what kind of symmetry things have, we have two options. We can either look at a graph or we can do it algebraically. So I'd like to end today just talking about both of those. Let's say, I look at these and I want to know if these are even, odd, or neither. So what kind of symmetry does this one have? If it's symmetric to the y-axis. If it's symmetric to the y-axis, we call that even. What kind of symmetry is this? Origin. And if it's symmetric to the origin, we call that odd. What kind of symmetry is this one? Origin, so that would be odd. This is symmetric to the, it's origin again. If you folded this over the y, it would look like that, and then if you folded it over the x, then it would overlap itself. So that one is again odd. Alright, so let's talk about if I just give you the function and ask you to decide if it's symmetric. Some of these we can use a graphing calculator for. But can I do x equals the absolute value of y on my graphing calculator? No. So we could make a t-chart and graph it ourselves. The other way to test symmetry to the x-axis, what you do is replace your y with a negative y and see if you get the same equation back. So you're basically just making the opposite variable negative. So if I plug in a negative y, what is the absolute value of a negative? Positive. Do I get back what I started with? Yes. So that means yes, this is symmetric to the x-axis. So what do you think I should do to check the y-axis? Make the x negative. So if I have a negative x equals the absolute value of y, is there anything I can do to get rid of that negative on my x? No. So there's nothing I can do to turn this back into my original. So is it symmetric to the y? No. To check the origin, you do both. Make your x a negative x and your y a negative y. So if I do that, my x is negative, my y is negative. I can't get rid of the negative on my x. The negative on my y would disappear. Is that the same as the original? No. So this one is symmetric to the x-axis, but none of the others.
Wouldn't we be able to tell if it's an origin if it's not equal to both of them?
Yes. No, it is possible if both the x and the y are no, the origin could still be yes. But if one of those is yes and one is no, then the origin will be no. Alright, let's look at B. So you could use a graph or we could do it by hand. Let's practice by hand again. So what do I do to check the x-axis? So we get negative y equals the absolute value of x minus 3. Is there any way to make that go away? No, so the x-axis is a no. The y-axis, you make your x negative. And what happens if you do the absolute value of a negative? So that is what I started with, so that one is a yes. For the origin, we do both. Now the negative inside my absolute value will go away, but the negative on my x will not. So that one is, again, a no. So this one was only symmetric to the y-axis. Okay, do you want to talk about using the graph for one of these? So you can keep doing what we're doing. On C, if I wanted to use the graph, if I wanted to use my graphing calculator, what would I need to do? So I could add my y over, and then subtract my 6. So then if you graph that, go to your graphing calculator. So we're graphing 2x minus 6. So if I look at that graph, if I fold it on the x-axis, does it overlap itself? No. If I fold it on the y-axis, does it overlap itself? No. If I folded both over the x and over the y, would it overlap? No. So what does this one mean? Yeah, there's no symmetry on this one. They all turn out to be no. Okay.
I think my graph's messed up.
Just hit zoom number 6 and it'll reset your window. D, if I tried to solve this one for y, subtract over my x squared. How do I get rid of a square on my y? If you add a square root, what else do you have to do? You have to do a positive and a negative. If you want to graph that on your calculator, what you actually have to do is enter two things. The first one would be the positive square root of 25 minus x squared. And the second one would be the negative. So you put the negative and then your square root. So then if I look at it, the total graph would be the two of these combined. So it's giving me a circle. Is this symmetric to the y-axis? Yeah. Is it symmetric to the x-axis? Yes. Is it symmetric to the origin? Yes. This one has all of them.
How do you put squared, like x squared into
You can either use the little square button right there, or you can do it to a power of 2. Either way. So you have to enter both the positive and the negative in that case. So you can do them by hand, or you can do them on the calculator. I don't have a lot of time left. I'm going to go ahead and stop. So I really only have one more example that we haven't covered anything quite like it yet. There is a handout posted on Classroom. We only have about 5 minutes. I want you to start that handout. I'm not going to collect it until the end of class tomorrow. You can really do everything except questions 6 through 9. That's the one example we haven't gotten to. So your assignment. Handout, I want you to skip 6 through 9. tomorrow.